The logistic equation is a famous equation proposed by someone called Verhulst in the late 1800s, and has been used ever since to model things as diverse as the number of cells or even the human population. And the logistic growth model says that the rate of change of population size given by dn dt is a function of the population size itself, g of n. And the function is a quadratic function of n, and it has two parameters, r and k. R and k are fixed numbers, but they would be different, say, for growing cell populations versus a human population. R is called the intrinsic growth rate, and k is called the carrying capacity. And what the question asks us to do is to construct a phase plot, that is g of n versus n, for the logistic equation. Now recall g of n is dn dt, so this vertical axis is going to be the rate of change of population growth, and then the horizontal axis will be the size of the population. It also asks us to sketch the solution trajectory for n of t versus t. So n is given here on the vertical axis, and the time is given here. And we're going to do that for different initial conditions. Okay, let's start off by sketching out the phase plot. And so we want to know what g of n looks like. The first thing we can do is calculate the equilibria. So 0 is equal to g of n hat is equal to r n hat 1 minus n hat over k. And we know that r is a positive parameter, and so either n is equal to 0 or 1 minus n over k is equal to 0. So putting the hats on the ends there, we have n hat is equal to 0 or n hat is equal to k. This first equilibrium is when there's no individuals in the population, and the second equilibrium is when the population is at carrying capacity. We can write g of n as Rn minus r n squared over k. And so if we want to know what the shape of g is, we can calculate the derivative. G prime of n is equal to r minus 2 r n over k, which is equal to r into 1 minus 2n over k. And so if g prime of n is equal to 0, then we're going to have that 1 minus 2n over k is equal to 0. And so that would imply that n is equal to k over 2. So this is a critical point. If we take the second derivative, g double prime of n, we can see that this is going to be equal to the derivative of r minus 2 r n over k, and that's going to be minus 2 r over k. And so n is equal to k over 2 gives a maximum. Okay, so we have the equilibria at n hat is equal to 0, and n hat is equal to k. Midway, we have the value k over 2, and this is going to be a maximum for g. And so our function looks like this. Okay, so when n is between 0 and k, g will be positive, i.e. dn dt will be greater than 0. When n is above k, our line for the function is negative, and so we have dn dt is less than 0. This allows us to put lines on the phase line diagram. So when dn dt is positive, n will be increasing, i.e. the arrows will be moving to the right. When n is larger than k, then dn dt will be negative, and the arrows will be moving to the left. When we plot the solution, n of t versus t, we use these axes here, n on the vertical axis and t on the horizontal axis. We can take these values of n that we have on the graph and put them on this graph. So we have 0, and let's put in k, and also k over 2. Let's consider a couple of different initial conditions. For the first one, we'll start with a value of n that lies above k. If we start off above k, we're up here on this graph. The population will decline because the arrow is moving to the left, and it'll approach the carrying capacity. So this is case 1. Let's start just to the left of the carrying capacity for our second initial condition. And here, our population will start on this axis just below k, and it's going to move to the right, and so the population is increasing until it gets to k. And so the curve will look like this. So that's number 2. Number 3, let's consider a population that starts just above 0. And so we're going to start right here on this axis. And the population is going to grow all the way up towards the carrying capacity. So we know when we draw this curve, it's got to approach this horizontal line here. But notice that the population growth rate is highest at n is equal to k over 2. So the value for dn dt is largest at this point right here. So as we draw this curve, we can make sure to include that feature as well. So dn dt is largest for n is equal to k over 2. dn dt is the slope of the tangent line to this curve. And so this is case 3. And you can see wherever we start, as long as we have a population size which is initially positive, it's going to move towards the carrying capacity as time goes to infinity. And this is when the population levels off and it cannot grow any further because it's using all the resources.